In the beginning there was nothing, no light, no matter, no time. Then, in an instant, the universe erupted into existence with a burst of unimaginable energy. This event, known as the Big Bang, created the very fabric of space and time. Temperatures soared to trillions of degrees as a seething soup of particles emerged: protons, neutrons, and electrons, the building blocks of everything we know. As the universe expanded, it began to cool, allowing these particles to combine and form the first simple elements, hydrogen and helium. A few 100 million years later, gravity gathered these gases into dense clouds that ignited to create the first stars. These celestial giants lit up the cosmos, forging heavier elements in their fiery cores and scattering them across space when they exploded as supernova. From these stellar remnants, galaxies began to form, with billions of stars swirling together like cosmic cities. Within one of these galaxies, the Milky Way, a tiny planet called Earth, would eventually take shape. But in these first moments, the universe was young, vast, and full of potential, a blank canvas awaiting the brushstrokes of time and evolution. This is where our story starts, just before the Big Bang. Buckle up, it's going to be an awesome ride. We're about to dive into the Big Bang, see the first moments of creation, and watch as the universe is born. Okay, so before the Big Bang, before time and space as we know it, there was something called the singularity. It's a really, really hard thing to imagine. Think of all the stuff in the universe, everything you can see and everything you can't, all squeezed into a tiny point, smaller than a grain of sand. But this wasn't any ordinary point. The laws of physics, the rules that usually govern how things work, didn't apply here. Time wasn't ticking. Space wasn't there. It was like a tiny seed waiting to grow into something huge. Think of a tiny seed that grows into a giant oak tree. The singularity was similar. It held everything needed to make stars, galaxies, planets, and even us. But what made this singularity appear in the first place? That's a question that still puzzles scientists today. Some think it came from a random burst of energy, like a tiny spark in the darkness. Others believe our universe is just one of many, popping up like bubbles in a glass of fizzy drink. We might never know for sure how the singularity got there, but it's the foundation of everything in our universe. Understanding the singularity is like reading the first page of the universe's story. It sets the stage for the amazing events of the Big Bang. It's a place of mystery and potential, a reminder that the universe is full of amazing things we are only starting to understand. From this tiny, super-dense point, something incredible happened, something we call the Big Bang. But forget about a big explosion in space, because that's not really what happened. The Big Bang was the expansion of space itself, and it's still expanding today. In less than a second, the universe went from incredibly small to mind-blowingly huge, and kept growing. It's hard to imagine how fast and massive this event was. Think of baking raisin bread. As the bread rises, the raisins move further apart. That's kind of what happened during the Big Bang, with galaxies like raisins moving apart as space stretched. During this early expansion, the universe was unbelievably hot, like a giant soup of energy and tiny particles constantly bumping into each other. There were no stars, no planets, no galaxies, just pure energy. But within this chaos, things were starting to organize. The fundamental forces of nature, the rules that control how matter and energy behave, began to appear. The Big Bang wasn't just an explosion, it was the birth of the laws of physics that shape our universe. It was the moment our universe started to become what it is today. In the very first moments after the Big Bang, the universe was ruled by laws we are only beginning to understand. This period, called the Planck Epoch, lasted for an incredibly short amount of time, a tiny fraction of a second. To give you an idea of just how short it was, imagine cutting a second in half and then in half again and again over 50 times. That's how short the Planck time was. During this time, the universe was a strange place, where all the forces of nature were combined into one super force. It's so extreme that our current understanding of physics can't fully explain it. We don't have all the tools yet to understand what happened in those first moments. But even though it was incredibly short, the Planck epoch was crucial. It set the stage for everything that came after, determining the basic properties of the universe, like how strong the fundamental forces are and even how many dimensions we experience. Think about baking a cake. The ingredients you use and how you mix them at the beginning will determine what the cake will taste and feel like in the end. Similarly, what happened during the Planck epoch shaped the universe we see today. It reminds us that even though we've learned so much about the universe, there are still many mysteries waiting to be discovered. As the universe expanded and cooled down, a crucial event took place. The fundamental forces separated from each other. Imagine one massive force controlling everything. Now picture this force splitting into different forces, each with its own unique properties. First came gravity, the force that pulls things together. It's why we stick to the Earth, why the moon orbits our planet, and why galaxies stay together. Then came the strong and weak nuclear forces, which work inside the nucleus of an atom. The strong force holds the nucleus together, while the weak force governs radioactive decay. Finally, electromagnetism emerged. This force is responsible for light, electricity, and magnetism. It's why we can see, communicate wirelessly, and have electricity in our homes. This separation of forces was a turning point for the universe. It brought order to the chaos, creating structure from a messy state. This paved the way for the formation of atoms, stars, and eventually life itself. Just imagine, without the separation of forces, our universe would be completely different. No stars to light up the night sky, no planets to call home, and no life to wonder about the cosmos. Chapter 5: Nucleosynthesis. The birth of elements as the universe got even cooler. It reached a temperature where protons and neutrons, the tiny particles that make up atoms, could finally combine. This process, called nucleosynthesis, wasn't random. It was a precise cosmic dance governed by the fundamental forces. Imagine a vast cosmic ocean of protons and neutrons constantly colliding and interacting. Most of these collisions didn't amount to much, but sometimes the conditions were perfect for something amazing to happen. When a proton and a neutron collided with just the right amount of energy, they could stick together, forming a deuterium nucleus, a heavier form of hydrogen. This was a big deal, the first step in creating elements heavier than hydrogen. Deuterium nuclei then combined with other protons and neutrons, forming helium, the second most common element in the universe. This process of nucleosynthesis went on for about 17 minutes, creating the light elements that make up the stars and galaxies we see today. By the time nucleosynthesis ended, the universe was about 75% hydrogen, 25% helium, and tiny amounts of lithium and beryllium. The heavier elements like carbon, oxygen, and iron, which are essential for life as we know it, would become later formed in the fiery cores of stars. While nucleosynthesis was busy creating the first elements, something incredible was happening on a much larger scale. The universe was expanding incredibly fast, a period called cosmic inflation. Imagine a balloon with tiny dots drawn on it. Now picture that balloon inflating incredibly quickly, faster than the speed of light. The dots representing galaxies would be pushed apart incredibly fast. That's basically what happened during cosmic inflation. In a tiny fraction of a second, the universe expanded exponentially, growing incredibly large. This rapid expansion smoothed out the fabric of space-time, explaining why the universe looks so uniform on large scales. Cosmic inflation also amplified tiny quantum fluctuations that existed in the early universe, stretching them to enormous sizes. These fluctuations acted like seeds for the large-scale structure of the universe, the clusters and superclusters of galaxies that we observe today. Imagine a calm pond. Cosmic inflation was like dropping a pebble into it, creating ripples that spread outward and changed the pond's surface. Cosmic inflation is a mind-boggling concept, but it's supported by a growing amount of evidence. It shows how powerful theoretical physics can be in explaining the universe's biggest mysteries. Chapter 7. Formation of matter and antimatter. In the early universe, there was a huge battle going on, a battle between matter and antimatter. For every particle of matter, there's an antiparticle with the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of energy. In the early universe's extreme conditions, particles and antiparticles were constantly being created and destroyed. It would seem like they would completely destroy each other, leaving nothing but energy. But then, something amazing happened. For every billion pairs of matter and antimatter particles, there was one extra particle of matter. This tiny difference, this slight excess of matter over antimatter, is why we exist today. As the universe cooled, matter and antimatter continued to annihilate each other. But because there was a little more matter, some of it survived. This leftover matter went on to form everything we see in the universe. Stars, planets, galaxies, and even us. The question of why there was this tiny imbalance between matter and antimatter is one of the biggest unsolved mysteries in physics. It's a question that takes us to the very limits of our understanding of the universe's fundamental laws. Thanks for joining me on this cosmic adventure. From the mind-blowing density of the singularity to the birth of the first atoms, we've seen the incredible events that shaped our universe. But our journey doesn't end here. The universe is still changing, still expanding, still full of mysteries to solve. Stay curious and keep exploring the wonders of the universe. Because like the great Carl Sagan said, somewhere, something incredible is waiting to be known. Black holes. These cosmic objects, shrouded in darkness yet capable of unimaginable power, have captivated scientists and dreamers alike for decades. In this video, we'll explore their mysteries, from their formation to their potential impact on the fate of the universe. Prepare to journey with us into the abyss, where gravity reigns supreme and the very fabric of space-time is distorted. So what exactly are black holes? Imagine a region in space where gravity is so strong that nothing, not even light, can escape. That, my friends, is a black hole, formed from collapsed stars. Their mass is concentrated into a singularity. This singularity is surrounded by the event horizon, the point of no return. Cross it and you're trapped forever. The life cycle of a star is a delicate dance between gravity and nuclear fusion. For most of a star's life, these forces are in equilibrium. But when a massive star exhausts its nuclear fuel, gravity gains the upper hand. The star's core collapses in on itself, triggering a cataclysmic explosion known as a supernova. This explosion can outshine entire galaxies, briefly illuminating the cosmos with unparalleled brilliance. If the core is massive enough, gravity will continue to crush it down until it collapses into an infinitely small point, a singularity giving birth to a black hole. Imagine the unimaginable pressure and heat as the core collapses, atoms themselves crushed into oblivion. The fabric of space-time contorts under the immense gravity, creating an event horizon around the singularity. The formation of a black hole is a testament to the immense power of gravity, a force that governs the cosmos on the grandest of scales. Black holes, like stars, come in different sizes. Stellar mass black holes, the most common type, are formed from the collapse of massive stars and typically have masses a few times that of our Sun. These cosmic remnants lurk throughout galaxies, often invisible unless they actively pull in surrounding matter. Then we have the behemoths, the supermassive black holes. These gravitational giants, millions or even billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. Their origins are still a mystery, but they play a crucial role in the evolution of galaxies, shaping their structure and influencing star formation. Astronomers also suspect the existence of intermediate mass black holes, a missing link in the black hole family. And let's not forget about primordial black holes, hypothetical objects thought to have formed in the very early universe, just moments after the Big Bang. Chapter 5. Singularity, the heart of the black hole. At the heart of every black hole lies the singularity, a point of infinite density where physics break down. Here, all matter is compressed into an infinitely small point where space and time cease to exist. Imagine all the mass of a star squeezed into a region smaller than an atom. Scientists believe gravity becomes infinitely strong, creating infinite curvature in space-time. This means our current theories can no longer describe what happens at the singularity. To understand the singularity, we need a new theory incorporating quantum mechanics and relativity. Despite our limited understanding, the singularity remains a captivating concept, a reminder of the profound mysteries within the universe. Chapter 6. How do we detect black holes? Black holes are invisible to conventional telescopes. We detect them by their gravitational influence. Observing their effect on nearby stars is one method. Another is detecting X-rays from accretion disks. Chapter 7. Hawking radiation. Black holes, once thought to be inescapable cosmic traps, may not be entirely black after all. In the 1970s, renowned physicist Stephen Hawking proposed a revolutionary idea that shook our understanding of these enigmatic objects. Black holes could actually emit radiation. This radiation, now known as Hawking radiation, arises from the bizarre world of quantum mechanics, the realm of the very small. According to quantum mechanics, empty space isn't truly empty, but is teeming with virtual particle pairs that constantly pop in and out of existence. Sometimes one particle might fall into the black hole while its partner escapes into space. The escaping particle carries away a tiny amount of the black hole's energy, causing the black hole to slowly lose mass over time. Over unimaginably long periods, Hawking radiation could cause black holes to slowly evaporate, eventually disappearing altogether in a final burst of energy. Chapter 8. Supermassive black holes in galaxies. At the heart of most galaxies, including our own Milky Way, lies a supermassive black hole. These giants, millions or billions of times the mass of our Sun, shape their galaxies. Imagine a cosmic whirlpool spiraling towards a central point. This is the accretion disk, where matter is drawn in by immense gravity. As material falls, it heats up, releasing energy from radio waves to X-rays. Active galactic nuclei can outshine entire galaxies. The relationship between galaxies and their black holes is a cosmic dance shaping the universe. Chapter 9. The first image of a black hole. For decades, black holes remained elusive objects. Their existence inferred from their gravitational effects, but never directly observed. Then, in 2019, a team of astronomers achieved the seemingly impossible. They captured the first ever image of a black hole. This monumental achievement was the culmination of years of effort from the Event Horizon Telescope EHT collaboration, a global network of telescopes working in unison to create a virtual Earth-sized telescope, capable of resolving incredibly small details on the sky. The image, a blurry but unmistakable ring of light surrounding a dark central region, confirmed what Einstein's theory of general relativity had predicted over a century ago, that black holes exist and warp space-time around them. This groundbreaking image wasn't just a technological marvel. It was a testament to the power of human curiosity, collaboration, and the relentless pursuit of knowledge. Let's embark on a thought experiment. A rather unpleasant one, to be honest. Imagine falling into a black hole. What would happen to you as you journey towards the unknown? The answer, my friends, is not pretty. It involves a process scientists affectionately call spaghettification. As you approach the black hole, The gravitational pull on your feet would be significantly stronger than on your head. This difference in gravitational force, known as tidal force, would stretch your body like spaghetti, hence the rather unappetizing name. As you fall further, the tidal forces would intensify, stretching you not just vertically but horizontally as well, squeezing you from the sides. You'd be elongated and compressed simultaneously, transformed into a long, thin stream of matter, spiraling towards the singularity. While this thought experiment might seem like pure science fiction, it highlights the extreme conditions found near black holes and the bizarre effects of their immense gravity. Black holes, with their immense gravity warping the fabric of space-time, have sparked some of the most mind-bending ideas in physics, including the possibility of wormholes and time travel. Wormholes, hypothetical tunnels connecting different points in space-time, are often depicted in science fiction as shortcuts through the cosmos, allowing for faster-than-light travel. While there's no observational evidence for their existence, Einstein's theory of general relativity does allow for the possibility of these space-time shortcuts. Imagine folding a piece of paper in half and poking a hole through both layers. That hole represents a wormhole, connecting two distant points on the paper. Similarly, a wormhole could potentially connect distant regions of space-time, allowing for travel between them that would otherwise be impossible. Time travel, another staple of science fiction, also finds a place in discussions about black holes. Einstein's theory of relativity suggests that time is not absolute, but is relative to the observer's frame of reference. As we gaze into space, we wonder about the universe's fate. Will it expand forever or collapse in a fiery big crunch? Black holes might hold clues to the universe's destiny. They could dominate, consuming matter and energy. Eventually, even black holes will evaporate. Thank you for joining us on this journey through the abyss. We've explored the bizarre world of black holes, from their formation in the death throes of massive stars to their potential impact on the fate of the universe itself. Imagine you're standing at the edge of the world, looking out into a never-ending emptiness. The feeling of awe and wonder is overwhelming. Now, imagine that emptiness isn't an ocean, but the very stuff that makes up space and time. It's a vast, dark expanse filled with mysteries. That's the exciting part about the edge of the observable universe, a place that makes us use our imaginations and pushes us to understand the vastness of space. It's a frontier that challenges our knowledge and curiosity. But what exactly is this observable universe? And what secrets hide at its mysterious edge? What lies beyond what we can see? The observable universe is everything we can see from Earth right now, including all the matter and energy within it. It's our cosmic neighborhood. It's like a giant ball with us at the center, stretching out for billions of light years in every direction. This sphere is filled with countless stars, galaxies, and cosmic wonders. The light from faraway objects like stars, galaxies, or even the faint glow left over from the Big Bang has had enough time to travel all the way to us since the universe began. This light carries stories from the distant past, but that doesn't mean we've seen it all. There are still countless mysteries waiting to be uncovered. Our view of the cosmos is limited by something called the cosmic horizon. It's the ultimate boundary of our observable universe. It's like a boundary that's set by how old the universe is and how fast light can travel. This boundary defines the limits of our cosmic vision. It's not a real wall, but more like a point in space and time beyond which we can't see. It's an invisible frontier. Light from beyond this horizon hasn't had enough time to reach us yet, so we can only wonder about the mysteries that are still hidden out there. What secrets do these uncharted regions hold? As the universe keeps expanding, this cosmic horizon expands too, slowly revealing more of the universe to our telescopes. Each new discovery brings us closer to understanding the cosmos. This constant expansion, combined with the fact that light travels at a certain speed, creates a fascinating puzzle. The observable universe is always getting bigger, but there will always be parts of the universe that we'll never be able to see. The quest to explore the unknown continues. Looking deep into the observable universe is like taking a trip back in time, a journey through the vast cosmic history. The farther away something is, the longer it took for its light to reach us, meaning we are seeing it as it was in the distant past. This gives us a unique glimpse of what the universe was like in the past, allowing us to piece together its history. This cosmic time machine takes us all the way back to the faintest light we can detect, the cosmic microwave background, or CMB, a relic from the early universe. The CMB is like a faint echo of the Big Bang, a whisper from the universe's infancy. It is a leftover from when the universe was very young, a snapshot of its earliest moments. It appeared about 380,000 years after the Big Bang, during a time when the universe was cooling down. This cooling allowed protons and electrons to join together and form hydrogen atoms, the building blocks of the universe. This process allowed light to travel freely for the first time, filling the universe with a special kind of radiation that we can still detect today. Today, we see this ancient light as a faint glow of microwaves, a remnant of the early universe. This signal is everywhere in space, a constant reminder of our universe's origins. The CMB is like a baby picture of the universe, showing us tiny differences in temperature. These temperature variations eventually became the seeds of the galaxies and galaxy clusters we see today, shaping the cosmos. But the CMB isn't the only thing that's been left behind from the early universe. There are other relics too. The James Webb Space Telescope, or JWST, has recently spotted galaxies so incredibly far away that they're changing our understanding of how galaxies form and evolve. These galaxies, some of which existed just a few 100 million years after the Big Bang, are providing new insights. They shine brightly in infrared light, a testament to their ancient origins. Their light has been stretched by the expansion of the universe, a phenomenon known as redshift, revealing the vastness of cosmic history. These early galaxies aren't just interesting to look at. They are like time capsules, offering a glimpse into the distant past. They give us important clues about how the universe has changed over time, evolving from a hot, dense state to the vast cosmos we see today. The fact that they existed so early in the universe's history challenges some of our ideas about how galaxies form, pushing the boundaries of our understanding. This suggests that galaxy formation might have been a much faster and more efficient process than we once thought, occurring in a cosmic blink of an eye. To figure out how far away these objects are and how old they are, astronomers use a technique called redshift. Redshift occurs as the universe expands, causing light waves traveling through it to get stretched out, making their wavelengths longer. This stretching makes the light look redder, which is why it's called redshift, a fundamental concept in cosmology. The bigger the redshift, the farther away the object is, and the longer its light has been traveling through the expanding universe, revealing its ancient origins. By measuring the redshift of distant galaxies and quasars, astronomers can create a timeline of the universe's evolution, mapping its history. This timeline traces the universe's expansion all the way back to the Big Bang, the moment of its birth. These observations have completely changed our understanding of the universe and our place in it, offering new perspectives. They tell us that we live in a dynamic and constantly changing universe, full of mysteries yet to be uncovered, where vast distances separate us from the very beginning of time, connecting us to the origins of everything we know. This journey through time and space continues to inspire and challenge our quest for knowledge. So, let's talk about something really cool: the shape of the universe. Figuring out whether the universe is flat, open or closed is one of the biggest questions in cosmology. Right now, our observations suggest that the universe is flat, but there's still so much more to discover. The shape of the universe affects everything from how light travels to what will eventually happen to the universe itself. It's a really mind-blowing thing to think about. Now let's talk about the James Webb Space Telescope and what amazing things it might discover. This incredible telescope is going to change everything we thought we knew about space. It's designed to see further back in time than ever before, all the way to the very first galaxies that formed after the Big Bang. The James Webb Space Telescope will also let us study the atmospheres of planets around other stars in amazing detail, and maybe even find signs of life. And this is just the beginning. The future of space exploration is full of possibilities, and who knows what incredible discoveries are waiting for us. Imagine for a second that our universe isn't the only one. Some theories suggest that we live in a multiverse, a massive collection of universes, each with its own set of rules and laws of physics. It's a pretty wild idea, right? This idea challenges everything we thought we knew about reality and opens up a whole world of possibilities. Could there be other versions of ourselves living completely different lives in these parallel universes? The mysteries are huge and the implications are truly mind-blowing. What will happen to our universe in the very, very distant future? Scientists have come up with a few different ideas about how it all might end. One possibility is the Big Freeze, where the universe keeps expanding, stars eventually die out, and galaxies drift farther and farther apart, leaving behind a cold, dark, and empty space. Another possibility is the Big Crunch, where the universe's expansion eventually reverses and everything collapses back in on itself into a single point. There's also the Big Rip, where the very fabric of space and time is torn apart. Each of these possibilities paints a pretty dramatic picture of the end of everything we know. The search for life beyond Earth is one of the most exciting and important things we're doing right now. From exploring Mars to studying distant planets around other stars, scientists are working hard to find any sign of life out there in the vastness of space. What if we're not alone? Finding extraterrestrial life would completely change our understanding of biology, evolution, and our place in the universe. It's a journey driven by curiosity and the desire to answer one of humanity's oldest questions. Are we alone? As we explore the universe, we seem to find more questions than answers. But it's this thirst for knowledge that makes us human. Our curiosity pushes us to explore, to understand, and to push the boundaries of what we know. We live on a planet called Earth, a small yet vibrant world teeming with life. It circles around a star we call the Sun, which provides the energy necessary for life to thrive. But our Sun is just one of billions of stars in the Milky Way galaxy. A vast collection of stars, planets, and cosmic dust. Imagine the Milky Way as a giant city filled with stars, each one potentially hosting its own solar system. Now imagine billions of these star cities scattered across space. That's our universe, an almost incomprehensible expanse. Some of these galaxies look like our Milky Way, with their spiral arms and dense cores, while others are completely different, taking on elliptical or irregular shapes. By learning about these faraway galaxies, we can understand our own place in the universe and uncover the secrets of how galaxies are born, evolve, and sometimes even collide. Our journey beyond the Milky Way starts with an amazing tool, the Hubble Space Telescope, a marvel of modern engineering. Launched in 1990, Hubble orbits high above Earth's atmosphere, free from the distortions caused by our planet's air. This special spot allows it to take incredibly clear pictures of distant objects in space, revealing details that were previously hidden from us. Hubble has completely changed how we see galaxies, showing us their true complexity and beauty. Its observations have shown us a universe more enormous and amazing than we ever imagined, expanding our understanding and igniting our curiosity about what lies beyond. The Hubble Space Telescope is like a time machine, looking back billions of years. It has captured light that has traveled for ages across the universe. This light carries secrets of the early universe. Hubble's pictures have allowed us to witness stars being born and galaxies taking shape. One of Hubble's most important discoveries was confirming the existence of supermassive black holes. These mysterious objects hide at the hearts of galaxies. Their gravity is so strong that nothing, not even light, can escape. Hubble gave us the first real proof that these cosmic giants are real. Hubble has also helped us measure the distances to faraway galaxies very accurately. This has been really important for figuring out how old the universe is. By studying the light from these distant galaxies, Hubble has helped us understand how the universe is expanding, getting bigger all the time. Black holes are some of the most fascinating things in the universe. They captivate our imagination and challenge our understanding of physics. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This makes them invisible to the naked eye, but their presence can be inferred by their effects on nearby matter. Supermassive black holes, millions or even billions of times heavier than our Sun, live in the centers of most galaxies. These colossal entities have a profound impact on their surroundings. Hubble played a key role in proving these cosmic giants exist. Its observations have provided us with invaluable data, helping us to understand the scale and influence of these black holes. By watching how stars and gas move around the centers of galaxies, astronomers figured out that these invisible giants must be there. The gravitational pull of these black holes affects the orbits of stars and the flow of interstellar gas. The pull of a supermassive black hole is so strong that it can make matter move incredibly fast, creating powerful jets of energy that can stretch for thousands of light years. These jets can influence the formation of new stars and the overall structure of the galaxy. These black holes are really important in how galaxies change and evolve. They can merge with other black holes during galaxy collisions, leading to even more massive black holes. They can influence where stars are born and control how their host galaxies grow. The energy and radiation they emit can trigger or suppress star formation in different regions of the galaxy. Studying these mysterious objects gives us important clues about the basic rules that shape our universe. By understanding supermassive black holes, we gain insights into the fundamental forces and processes that govern the cosmos. Discovering planets beyond our solar system, called exoplanets, has been one of the most exciting things to happen in astronomy. Hubble has played a big part in this search, observing the atmospheres of exoplanets as they pass in front of their stars. While Hubble has mostly focused on exoplanets in our Milky Way galaxy, there's growing evidence that planets might exist in other galaxies too. Finding these extragalactic planets is really hard, but it's not the end of the world. Finding planets in other galaxies would be an amazing discovery. It would suggest that planets are common throughout the universe, making it more likely that life might exist beyond our Milky Way. Galaxies come in an amazing variety of shapes and sizes. The most familiar types are spiral galaxies, like our own Milky Way, with their elegant arms and central bulges. Elliptical galaxies, on the other hand, are smooth and oval-shaped, without the spiral arms. Hubble has captured stunning images of galaxies of all shapes and sizes, revealing just how diverse these cosmic islands are. Some galaxies are busy making new stars, while others are relatively quiet. Some galaxies are locked in gravitational dances with their neighbors, their shapes distorted by the forces pulling on them. Studying the different types of galaxies and their characteristics helps us understand how these systems form and change over billions of years. By observing galaxies at different distances, we can piece together a timeline of galaxy evolution throughout the universe's history. In the 1920s, astronomer Edwin Hubble made an amazing discovery. The universe is expanding. This means that galaxies are moving away from each other, and the farther apart they are, the faster they are moving away. Hubble's observations of distant galaxies provided more proof of this expansion. By measuring how much the light from these galaxies has stretched, astronomers were able to determine their speeds and confirm that they are moving at the same, and confirm that the universe is indeed getting bigger. This expansion has huge implications for our understanding of how the universe began and what will happen to it in the future. The discovery of the universe's expansion completely changed our view of the cosmos. It suggests that the universe began from a single point known as the Big Bang and has been expanding and evolving ever since. The Hubble Space Telescope hasn't just changed how we understand the universe, but it has also inspired generations of scientists, engineers, and everyday people. Its stunning images have become famous, capturing the beauty and wonder of space and sparking our imaginations. Hubble's legacy goes beyond its scientific discoveries. It has shown the power of human creativity and teamwork in unlocking the secrets of the universe. Its success has paved the way for future space telescopes like the James Webb Space Telescope, which will push the limits of our knowledge even further. Hubble's impact on our understanding of the universe is immeasurable. It has revealed a cosmos more vast, more diverse, and more awe-inspiring than we ever imagined. Its legacy will continue to inspire us for generations to come. Trying to understand the universe is a never-ending journey of exploration and discovery. Each new observation, each new piece of information brings us closer to uncovering the mysteries of the cosmos. From the tiniest particles to the largest structures, the universe is a tapestry woven together by the fundamental laws of physics. The Hubble Space Telescope, along with other telescopes on Earth and in space, has given us an amazing view of this grand tapestry. We have witnessed stars being born and dying, galaxies forming and evolving, and the intricate dance of gravity that shapes the fabric of space-time. These discoveries haven't just deepened our understanding of the universe, but have also raised new questions and challenges, pushing the limits of human knowledge and imagination. As we stand at the forefront of astronomical discovery, we are reminded of the vastness of the universe and our small yet significant place within it. The future of space exploration is full of possibilities, each more exciting than the last. New and more powerful telescopes, equipped with advanced technology, both on Earth and in space, will allow us to peer deeper into the cosmos than ever before. These instruments will continue to reveal the secrets of the cosmos, uncovering mysteries that have puzzled humanity for centuries. Looking deeper into the universe, we will find new phenomena and perhaps even new forms of life. These discoveries will show us its hidden wonders, expanding our understanding of the cosmos. We will continue to explore our own solar system, sending missions to distant planets and moons. Probes will venture to the far reaches, gathering data and searching for signs of life. Scientists will analyze this data, piecing together the history of our cosmic neighborhood. Each discovery will bring us closer to understanding the origins and evolution of our solar system, and we will continue to look out into the vastness beyond, driven by an unquenchable thirst to understand our place in the grand scheme of the universe. The quest to understand the universe is an ongoing adventure, a journey that will continue to inspire and challenge us for generations to come. As we explore the cosmos, we discover not only the wonders of the universe, but also the limitless potential of the human spirit. This journey of exploration and discovery will continue to push the boundaries of our knowledge and imagination. As we explore the cosmos, we uncover the mysteries of the universe and the boundless potential of humanity. We discover not only the wonders of the universe, but also the limitless potential of the human spirit. The unending quest for knowledge and understanding will continue to drive us forward, inspiring future generations to reach for the stars. The universe is massive and full of secrets. It's a vast expanse that stretches beyond our imagination, filled with wonders and mysteries that have intrigued humanity for centuries. It has billions of galaxies, each one a colossal collection of stars, planets, and cosmic dust, all bound together by gravity, and each one has billions of stars. These stars vary in size, color, and temperature, creating a dazzling array of celestial bodies. But how did it all start? This question has puzzled scientists and philosophers alike for generations. The best explanation we have is the Big Bang. This theory suggests that the universe began as an incredibly hot and dense point, which then expanded rapidly. It all began with a tiny speck, even smaller than an atom. This minuscule point contained all the matter and energy that would eventually form everything we know today. This speck was packed with so much stuff and heat it's hard to imagine. Then it exploded. This explosion wasn't like any explosion we're familiar with. It was the birth of space and time itself. Around 13.8 billion years ago, this explosion kick-started our universe. From that moment, space began to expand, and it has been growing ever since. But it wasn't like a regular explosion, like a firework. Instead, it was a rapid expansion of space itself, carrying galaxies along with it. Instead, it was like space itself was stretching and growing. Imagine the fabric of the universe being pulled apart, creating more and more space as it expands. Imagine a balloon with dots on it. As you blow air into the balloon, the dots move further apart, right? This is a simple way to visualize how the universe expanded. When you blow air into the balloon, the dots move further apart, right? Similarly, as the universe expanded, galaxies moved away from each other. That's what happened in the Big Bang. Space expanded, taking galaxies along for the ride. This expansion continues even today, with galaxies drifting further apart. How do we know about the Big Bang? Scientists have gathered evidence through observations and experiments. Scientists have seen that the universe is still expanding, with galaxies moving away from each other. This observation supports the idea that the universe started from a single point. They've also found a faint glow left over from the Big Bang called the cosmic microwave background radiation. This radiation is a remnant of the early universe, providing a snapshot of its infancy. It's like a baby picture of the universe showing us what it looked like a really long time ago. This baby picture helps scientists understand the conditions of the early universe. The Big Bang theory is a big deal in science. It provides a comprehensive explanation for the origin and evolution of the universe. It explains how our universe went from being super-duper tiny and hot to the amazing cosmos we see today. This transformation is a testament to the incredible forces at work in the universe. As we learn more about the Big Bang, we understand more about the laws of nature and our place in this giant universe. Each discovery brings us closer to unraveling the mysteries of our cosmic origins. At the heart of the Big Bang theory is something really strange and fascinating: the primordial singularity. This concept is not just a cornerstone of cosmology, but also a profound mystery that challenges our understanding of the universe. Imagine everything in the universe squashed into a single point, unbelievably dense and hot. That's the singularity. It's a mind-boggling idea where all the matter, energy, and even the fabric of space-time itself were compressed into an infinitesimally small point. It's a point where our current understanding of physics just can't keep up. The laws of physics as we know them break down, and we enter a realm of unknowns and paradoxes. The singularity is a place of extremes. Temperatures and densities reach unimaginable levels, far beyond anything we can replicate or observe directly. Time, as we know it, didn't exist before it. The very concept of time emerges from this singularity, marking the beginning of everything we experience. Space was also squeezed into this point. The vast, seemingly infinite universe we see today was once confined to an incredibly tiny volume, and all the forces of nature, like gravity and electromagnetism, were combined into one superforce. This unification of forces is something physicists are still trying to understand. The singularity is a puzzle that scientists are still trying to solve. It represents the limits of our knowledge and the frontier of modern physics. Some believe it wasn't actually a point, but a very, very tiny and dense region. This idea opens up new possibilities for understanding the early universe. Others think the universe didn't start with a singularity at all, but from a previous universe shrinking. This cyclical model suggests a series of expansions and contractions over time. Even though it's a mystery, the singularity is important for understanding how the universe began. It provides a crucial clue in the quest to unravel the origins of everything. It's like the edge of our knowledge. Beyond it lies the unknown, waiting to be discovered. As we explore space and the Big Bang, maybe one day we'll unlock the secrets of the primordial singularity. This journey of discovery is what makes science so exciting and endlessly fascinating. right after the Big Bang, things were super chaotic and energetic. The universe was a boiling cauldron of energy and particles, constantly colliding and interacting in ways that are hard to imagine. This time, from the Big Bang until about 10 to the negative 43 seconds, is called the Planck epoch. It's a period so brief yet so crucial that it set the stage for everything that followed. It was so extreme that our current understanding of physics can't fully explain it. The laws of physics as we know them break down, and new theories are needed to describe what happened. During this time, the universe was tiny, even smaller than an atom. Imagine all the matter and energy of the universe compressed into a space so small it's almost incomprehensible. Temperatures were off the charts, reaching trillions and trillions of degrees. These extreme conditions were unlike anything we can experience or replicate on Earth. At these insane energies, all the forces of nature were combined into one superforce. This means gravity, electromagnetism, and the nuclear forces were unified, acting as a single entity. The Planck epoch is where quantum mechanics, the rules for tiny particles, meet gravity, the force that governs big stuff like planets and stars. This intersection is a frontier of modern physics. Understanding how these two work together is a huge challenge for scientists. It's like trying to piece together a puzzle with missing pieces, where each discovery brings new questions. Even though the Planck epoch is mysterious, it holds clues about how the universe works at its most basic level. These clues are essential for unlocking the secrets of the cosmos by studying what's left over from this era. Like the cosmic microwave background radiation, scientists hope to figure out what happened during this crazy time. For a long time, people thought the universe was still and unchanging, like a beautiful painting that never changed. But in the 1900s, we discovered the universe is much bigger and more exciting than we ever thought. Today, we'll explore how we know the universe is growing and what that means for the future. Our story starts in the 1920s with Edwin Hubble at the Mount Wilson Observatory. This was a time of great discovery and innovation in the field of astronomy. Hubble, a pioneering astronomer, was using one of the most powerful telescopes of his time to peer deep into the cosmos. Hubble was studying the light from faraway galaxies and noticed something strange. He meticulously recorded the light spectra from these distant celestial bodies, hoping to unlock the secrets of the universe. The light waves were stretched out, making them look redder. This phenomenon puzzled Hubble at first, but he soon realized it was a crucial clue. This is called redshift, and it happens when things move away from us. Redshift is a key concept in understanding the movement of galaxies. It occurs because the wavelength of light is stretched, shifting it towards the red end of the spectrum. The farther away a galaxy was, the more redshifted its light was, meaning it was moving away faster. This observation was groundbreaking. It suggested that the universe was not static as previously thought, but dynamic and ever-changing. Hubble realized something amazing. The universe wasn't still. It was expanding. This was a revolutionary idea that changed our understanding of the cosmos forever. The implications were profound, suggesting that the universe had a beginning and has been growing ever since. Like dots on a balloon being blown up, galaxies are moving apart as space itself stretches. This analogy helps us visualize how space expands, carrying galaxies with it. The discovery of the expanding universe opened up new avenues of research and led to the development of the Big Bang theory, which posits that the universe began from an incredibly hot and dense state and has been expanding ever since. The Big Bang theory is now the leading explanation for the origin of the universe. It provides a comprehensive framework for understanding the evolution of the cosmos from its earliest moments to the present day. Hubble's discovery of the expanding universe was a pivotal moment in the history of science, reshaping our view of the cosmos and our place within it. Today, astronomers continue to build on Hubble's legacy, using advanced telescopes and technology to explore the farthest reaches of the universe. Each new discovery brings us closer to understanding the vast and mysterious cosmos we call home. Think about the sound of a police siren. As it comes closer, the sound is high-pitched. As it goes away, the sound gets lower. This is the Doppler effect. It happens with light too. When something in space moves away, its light waves stretch, shifting towards the red end of the spectrum. That's redshift. The faster it moves, the bigger the redshift. By measuring redshift, astronomers could tell how fast galaxies were moving and prove Hubble's discovery. For many years, scientists thought the universe's expansion was slowing down because of gravity. But in the late 1990s, we learned something surprising. The expansion wasn't slowing down, it was speeding up. This shocked everyone. What was causing this? Scientists think it's something called dark energy. Dark energy is like anti-gravity, pushing everything apart faster and faster. When we look into space, we're looking back in time. Light from faraway galaxies takes billions of years to reach us, but we can only see so far. The observable universe is everything we can see since the Big Bang. Beyond that is a huge unknown space, maybe even infinite. Light from those places hasn't reached us yet, so we can only wonder what's out there. Chapter 5, Echoes of the Big Bang, the cosmic microwave background. If the universe is expanding, it must have been much smaller and hotter in the past. Imagine a time when everything we see today was compressed into a tiny, incredibly dense point. This is the essence of the Big Bang theory, which suggests that the universe has been expanding ever since that initial explosion. We know this because of something called the cosmic microwave background, or CMB. The CMB is a crucial piece of evidence that supports the Big Bang theory. It acts like a snapshot of the infant universe, providing us with invaluable information about its early stages. Discovered in 1964 by Arno Penzias and Robert Wilson, the CMB is like a faint afterglow from the Big Bang. This discovery was accidental. They were actually trying to eliminate noise from their radio antenna, but stumbled upon this groundbreaking evidence instead. It's a type of radiation that permeates all of space. This radiation is incredibly uniform, but it has tiny fluctuations that tell us a lot about the early universe. These fluctuations are like fingerprints, each one a clue to the conditions that existed just moments after the Big Bang. It started just 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. Before this time, the universe was a hot, dense plasma where light couldn't move without being scattered. As it expanded and cooled, atoms formed, allowing light to finally break free and travel across the cosmos. The CMB shows us what the early universe looked like, with tiny temperature differences that became the galaxies we see today. These temperature variations are incredibly small, but they were enough to cause matter to clump together under gravity, eventually forming stars, galaxies, and all the structures we observe in the universe. Scientists study the CMB using satellites and ground-based telescopes. By analyzing this ancient light, they can learn about the universe's composition, its rate of expansion, and even its ultimate fate. The CMB is like a cosmic blueprint, offering a glimpse into the universe's past and helping us understand its future. The study of the CMB has led to numerous discoveries, including the realization that the universe is not only expanding, but accelerating in its expansion. This has profound implications for our understanding of dark energy, a mysterious force driving this acceleration. In essence, the cosmic microwave background is a time capsule, a relic from the dawn of time that continues to illuminate the mysteries of our universe. It reminds us of our origins and inspires us to keep exploring the cosmos, seeking answers to the fundamental questions of existence. The shape of the universe is linked to its future. The way the universe expands and evolves is deeply connected to its geometry. This geometry is not just a theoretical concept, but a fundamental aspect that determines the fate of everything within it. Is it flat like a piece of paper or curved like a ball or a saddle? These shapes are not just abstract ideas. they represent different possible realities for our universe. A flat universe suggests a precise balance, while a curved universe, whether positively or negatively, implies different destinies. The answer depends on how much stuff is in the universe. By stuff, we mean all the matter and energy that exists, including dark matter and dark energy. These components influence the overall curvature and expansion rate of the universe. If there's enough stuff, gravity will stop the expansion and make the universe collapse. The Big Crunch. This scenario envisions a universe that eventually contracts, leading to a dramatic and fiery end where all matter is pulled back into a singular point. If there isn't enough stuff, the universe will expand forever, the Big Freeze. In this case, galaxies will drift apart, stars will burn out, and the universe will become a cold, dark, and desolate place with temperatures approaching absolute zero. Right now, it looks like the universe is flat, meaning there's a balance between expansion and gravity. This balance suggests that the universe will continue to expand, but at a rate that slows down over time, never quite reaching a complete halt or collapse. This delicate equilibrium is a fascinating aspect of cosmology, offering insights into the ultimate fate of the cosmos. What will happen to the universe in the end? Will it expand forever, becoming cold and empty? Will dark energy get stronger and tear everything apart in a big rip? Or is there something else we can't even imagine? As we learn more about space, we understand more about our place in it, even though everything might eventually end. Our universe is huge and mysterious. From Earth, we can see faraway stars and galaxies, like leftovers from a universe born billions of years ago. Where did it all begin? How did it become what we see today? And the biggest question, how will it all end? Trying to solve this cosmic puzzle has led to some really interesting theories. Come with us on a journey to the edge of what we know as we explore how the universe might end. One of the coolest things about studying the universe's fate is how incredibly huge everything is. We're talking about timescales way longer than the life of our planet, our sun, and even our galaxy. Even though it's tough, scientists have learned a lot about how the universe has changed over time. By watching faraway galaxies move, we can see the effects of dark matter and dark energy. These forces that shape the universe's future. The universe's story is still being written. And as we look at the possibilities, we'll understand more about the amazing beauty and mysteries of everything around us. Imagine the universe not getting bigger, but smaller. That's the Big Crunch theory, a fascinating but scary idea about how the universe might end. Gravity, the same force that keeps us on the ground, would pull everything back together. As gravity gets stronger, the universe stops expanding and starts shrinking. The Big Crunch theory depends on something called critical density. If the universe is dense enough, gravity wins and pulls everything back together. But figuring out if the universe is dense enough is really hard. Scientists learned in the late 1990s and early 2000s that the universe isn't slowing down like it should if it was mostly matter. It's actually speeding up, pushed by a mysterious force called dark energy. Even though the universe is speeding up, some scientists still think the Big Crunch is possible. They think we don't understand dark energy completely and its effects might change over time. But most scientists think the Big Crunch is unlikely. We have lots of proof for dark energy, from exploding stars, the leftover heat from the Big Bang, and how galaxies are spread out. Even if it's not the most likely ending, studying the Big Crunch has taught us a lot. The Big Crunch is a dramatic ending, but heat death is different. But just as important, instead of a big crash, heat death is a slow fade where everything becomes the same temperature and nothing much happens. Think of a hot cup of coffee. It cools down until it's the same temperature as the room. The universe is like that coffee. As it gets bigger and older, the energy from stars and galaxies spreads out and fades away. Stars, the giant furnaces of the universe, don't last forever. When entropy is at its highest, the universe will be totally different. The beautiful stars and galaxies will be gone. All that will be left is a cold, dark space with a few particles too weak to do anything. The universe will be the same temperature everywhere, and no more energy can move around. It will be like a graveyard of dead stars and black holes slowly fading away. Time will almost stop meaning anything. The idea of heat death, a universe that never changes, is hard to accept. So some scientists think there might be other ways the universe could avoid this fate. Maybe the universe expands and shrinks in cycles with a big crunch followed by a new big bang. Or maybe tiny changes in empty space could start a new universe. The search for how the universe will end isn't over, and the answers might surprise us. The Big Rip theory is a different kind of ending, where the universe is torn apart by dark energy. Imagine a piece of cloth stretched tight. If you pull too hard, it rips. In this theory, dark energy gets stronger and stronger, pulling everything apart faster and faster. This would be a dramatic and destructive end. The Big Rip depends on a very strong kind of dark energy called phantom energy, which is even more mysterious than regular dark energy. Unlike regular dark energy, phantom energy keeps getting stronger and more powerful over time. This makes the universe expand faster and faster, leading to the catastrophic event known as the Big Rip. Scientists use something called the equation of state to understand how dark energy works and predict its future impact. The Big Rip is possible, but we don't know for sure. We know the universe is expanding faster, but we don't know enough about dark energy to say if it's phantom energy. Some scientists think we'll find out more in the future. Others think the Big Rip idea depends on our current understanding of physics, which might not be right in extreme situations. Whether the universe rips, fades, or ends some other way, the search for answers continues to amaze scientists and everyone else. We don't like the idea of a definite ending, so we often think about renewal. The concept of an ending can be unsettling, as it implies a finality that leaves no room for continuation or hope. This is why many cultures and philosophies have embraced the idea of cycles, where endings are merely new beginnings in disguise. The Big Bounce theory offers a hopeful alternative. Instead of a universe that ends in a cold, dark void, it suggests a universe that is constantly renewing itself. This theory provides a sense of continuity and eternal existence, which can be comforting. It says our universe isn't a one-time thing, but part of a never-ending cycle of expansion and contraction, death and rebirth. This cycle is akin to the changing seasons on Earth, where winter's death gives way to spring's rebirth. The universe, in this view, is a dynamic living entity, constantly evolving and transforming. Imagine the universe expanding, then stopping and collapsing back on itself, not into nothingness, but into a new Big Bang. This collapse is not an end, but a transition, a prelude to a new beginning. The energy and matter from the old universe are recycled into the new one, creating a seamless flow of existence. This is the Big Bounce, a cosmic dance where one universe ends and another begins. It's a beautiful, poetic vision of the cosmos, where destruction and creation are two sides of the same coin. Each bounce is a testament to the resilience and adaptability of the universe. Some scientists think this is possible because of quantum gravity, which combines Einstein's theory of gravity with the weird world of quantum mechanics. Quantum gravity attempts to bridge the gap between the macroscopic world of general relativity and the microscopic world of quantum physics, offering a unified understanding of the universe's fundamental forces. They think the center of a black hole could be the start of a new universe. In this scenario, the singularity at the heart of a black hole, where gravity is infinitely strong, could serve as a seed for a new cosmic expansion. This idea challenges our conventional understanding of black holes as mere endpoints. Also, the leftover heat from the Big Bang, called the cosmic microwave background radiation, could have marks from a previous universe, setting up our own. These marks, or anomalies, in the cosmic microwave background could be the fingerprints of a past cosmic cycle, providing clues about the universe's eternal journey through time. The Big Bounce is a hopeful idea, suggesting that the universe could collapse and then expand again in a never-ending cycle. However, other theories propose a more abrupt and unsettling end to the universe, driven by the strange and unpredictable nature of quantum mechanics. One such theory is vacuum decay, a concept that has intrigued and terrified scientists in equal measure. Imagine our universe is like a house of cards, seemingly stable but ready to collapse at any moment. This analogy helps us grasp the delicate balance that holds our universe together. In this theory, empty space isn't really empty. Instead, it's teeming with quantum fields that are the foundation of all particles and forces. These fields are constantly fluctuating, creating a dynamic and ever-changing backdrop to our universe. These quantum fields can exist at different energy levels. Our universe might currently be in a high-energy state known as a false vacuum. This state is not the most stable one, but it has persisted for billions of years. A lower energy state called a true vacuum might exist somewhere in the vast expanse of space. This true vacuum is more stable than our current state, and the universe naturally tends to move towards stability. If a random part of our universe were to transition to this lower energy state, it would create a bubble of true vacuum. This bubble would expand at the speed of light, consuming everything in its path and fundamentally altering the fabric of our universe. The terrifying part is that there would be no warning. The transition would be instantaneous, and the universe as we know it would vanish in the blink of an eye, leaving behind a completely different reality. This is a scary idea, one that challenges our understanding of the universe and our place within it. However, it's important to note that there's no concrete evidence to suggest that vacuum decay is imminent or even likely to happen. For now, it remains a fascinating yet unsettling possibility in the realm of theoretical physics. The universe is amazing and full of possibilities. How it will end is still a big mystery. Will it collapse, fade, rip apart, or be reborn? Right now, we think heat death is most likely, where the universe keeps expanding and cooling down. But science is about exploring all possibilities. New telescopes are looking deeper into space, and scientists are working hard to understand dark matter, dark energy, and quantum gravity. The end of the universe, however, it happens, reminds us how vast everything is, how connected everything is, and how special our time in the universe is. We've looked at many possible endings for the universe, some amazing and some scary. The universe, with its vastness and mysteries, has always intrigued scientists and philosophers alike. From the fiery cataclysms to the gentle fades, each potential end tells a different story about the cosmos and our place within it. The Big Crunch is a fiery end, where the universe's expansion halts and reverses, causing everything to collapse into a singular point, much like a reverse Big Bang. This scenario paints a dramatic picture of a universe that ends in a blaze of glory, with galaxies, stars, and planets all converging into an intense, hot, and dense state. The Big Rip is a violent one, where dark energy's influence grows so strong that it tears galaxies, stars, and even atoms apart. Imagine a universe where the very fabric of space-time is pulled to its limits, resulting in a chaotic and destructive end. This scenario is both fascinating and terrifying, as it suggests a universe that is torn apart at its very seams. And the Big Bounce is a hopeful one. In this scenario, the universe undergoes a cycle of expansion and contraction, leading to repeated Big Bangs and Big Crunches. This cyclical model suggests that the universe is eternal, constantly renewing itself in an endless loop of creation and destruction. It's a vision of a cosmos that never truly ends, but rather continually evolves. But based on what we know, heat death is the most likely. This scenario, also known as the Big Freeze, envisions a universe that slowly fades away as it expands. Over time, stars burn out, galaxies drift apart, and the universe cools down to a state of no thermodynamic free energy. This slow fading into a state where nothing much happens fits best with what we see and the laws of physics. As the universe continues to expand, it becomes increasingly cold and dark, with stars eventually burning out and galaxies becoming isolated. The universe is expanding faster because of dark energy, a mysterious force that makes up about 70% of the universe. This acceleration means that galaxies are moving away from each other at an ever-increasing rate, leading to a future where the night sky is devoid of stars, which means it will probably keep expanding and cooling. Stars will die, galaxies will move apart, and the universe will become a vast, empty, and cold expanse. The once vibrant and dynamic cosmos will transform into a quiet and desolate place, and the universe will become cold and dark. In this distant future, black holes will dominate, slowly evaporating over trillions of years, leaving behind a universe filled with low-energy photons and neutrinos. That death might seem sad as it represents a universe where all activity ceases. However, it also highlights the incredible journey of the cosmos, from the explosive birth of the Big Bang to the serene stillness of its end. But it shows how much the universe changes over vast amounts of time. The universe is a dynamic and ever-evolving entity, constantly undergoing transformations that span billions of years. Just like it started with the Big Bang and created stars and galaxies, the universe has always been in a state of flux, with each phase bringing new wonders and mysteries. It will keep changing, even after we're gone. The story of the universe is far from over, and its future, though it may seem bleak, is just another chapter in its grand narrative. But the universe's story isn't finished yet. We're always learning new things. New telescopes will help us understand dark energy better. Learning more about quantum gravity could teach us about black holes and the early universe. The idea of a multiverse, where our universe is just one of many, makes things even more complicated. If there is a multiverse, the end of our universe might not be the end of everything, but a new beginning. For now, the universe's fate is a mystery that continues to inspire us. As we explore the cosmos, we know that the universe is full of surprises, and the answers might be more amazing than we can imagine. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more cosmic explorations. We'll continue to unravel the mysteries of the universe, bringing you closer to the wonders of the cosmos. Until next time, keep looking up.